Hi APStat students. This will be another long section because there's a lot in here, so I suggest that you break it up into chunks and make sure you understand each part separately. First thing we need to do is talk about the sampling distribution of the difference of two means. Based on information from the U.S. National Health and Nutrition Examination Survey, the heights of 10-year-old girls follows a normal distribution with a mean of 56.4 inches and a standard deviation of 2.7 inches. The heights of 10-year-old boys follows a normal distribution with a mean mu of 55.7 inches and a standard deviation of 3.8 inches. Suppose we take independent, simple random samples of 12 girls and 8 boys of this age and measure their heights. What can we say about the difference in the average heights of the sample of girls and the sample of boys? Well, we know that we have normal populations, so we know that the shape, even though we're taking the difference, the normal minus a normal, will give us a normal sampling distribution. We know the center is going to be the difference in the males and females, so it would be the difference in the females minus the males. So we know that the females is 56.4 and then minus 55.7 for the males. Remember, these are 10-year-olds, so the girls are typically a little taller than boys. So this is 0.7 inches. Okay, and then the spread of the distribution, remember from our transformations, even though we're subtracting, we add our variances. So our standard deviation of the difference will be 2.7 squared over 12 girls plus 3.8 squared, and then it was square root of n, but remember we squared all that, over 8. This is all square rooted. So this is 1.55. Okay, we want the probability of getting a difference in sample means that's less than 0. So if we draw a picture, well, now that we have our picture, we can find this probability. Which is 33% roughly. So we want to know, do the results in part A give us reason to doubt the researchers' stated results? So remember, can we say about the difference in the average height of sample girls and the sample of boys? Well, we wanted to know what's the probability that the boys would be taller than the girls because it's a difference where the female minus the male is less than 0. Well, this says that it's not that rare. So it's not that rare that boys are taller than girls, meaning girls are not significantly taller than boys. So when population distributions are normal, the sampling distribution is normal, right? We already knew that. In other cases, the sampling distribution will be normal if, now we have the same situations that we've seen over and over again, N1 and N2, right, from our different sample sizes are greater than or equal to 30, or if they're both greater than or equal to 15 and no major skewness or outliers, or remember, if it's greater than 5 and the sample looks approximately normal. The mean of the sampling distribution is always that mean difference, right? Mu1 minus mu2, or mu2 minus mu1, it doesn't really matter. So that means the difference is an unbiased estimator of the difference in population means. The standard deviation of the sampling distribution is that formula, remember? Right here. S1 squared over N1 plus S2 squared over N2. Or if we know the population, then it would be sigma 1 squared over N1 plus sigma 2 squared over N2 square rooted. Okay, so now we have the two sample t interval, right? It's the same confidence interval that we've done, except now that we subtract, we have our statistic, which is our x1 minus x2, x bar 1 minus x bar 2. We have our critical value, which is our t star in this case. And then we have our standard deviation of the statistic, which is from there, remember, of the s's. Because in this case, we won't know the population standard deviation. Okay, so then we have our conditions. We need to check our random condition. We need our normal condition. Remember all those things that we just talked about from up here. And our independent condition, or the 10% condition, which will be most of it. Either both samples need to be independent, or both samples need to meet the 10% condition, less than 10% of the population. So, Mrs. Furlong is curious about the mean length of daisies and carnations. She took a sample of 35 carnations given to the performers at FHHS's production of Hairspray. The carnations had a mean length of 16 inches with a standard deviation of 2.73 inches. She also took a sample of 32 daisies, which had a mean length of 19 inches with a standard deviation of 3.21 inches. We need to construct and interpret a 95% confidence interval for the difference in mean length of daisies and carnations. Okay? It doesn't really matter which one we subtract from the other because we're looking for the difference, but we're going to label it. So we're going to state our procedure. We're going to do a 2 sample t interval, and then we need our context for mean difference in length of flower. So we have our conditions. We need to check our random condition. Well, she took a sample of these roses and she took another sample. We don't know, it doesn't say that they were random samples, but we will assume it. Then we need to check their normal conditions. Well, N1 is 35, N2 is 32. Both sample sizes are greater than or equal to 30, so we know that the sampling distribution is approximately normal. And then our independent condition, well, we can assume that 35 and 32 are less than 10% of each population. 35 is less than 10% of all carnations, and 32 is less than 10% of all daisies. So we're meeting our independent condition as well. Then we can use our calculator to do all of this stuff. We're going to go to Menu, Statistics, Confidence Intervals, and it's a 2 sample t interval. So we don't have the data, we have statistics. Okay, you'll do ones with both. We'll do our carnations first. So they had a mean length of 16 with a standard deviation of 2.73, and there was 35 carnations. Then we'll do our daisies. Our daisies had 19-inch length, so a little bit longer, with a standard deviation of 3.21, which is, so that seems pretty high. So I don't know if this will be a significant difference. And then remember we had 32 daisies. We wanted a 95% confidence interval, and we're not going to pool. So here are all of our data pieces. So we know that our interval is from negative 4.46 to negative 1.53. And we are 95% confident that the interval from negative 4.46 to negative 1.54 captures the true mean difference in flower length So what this means is that our interval does not have 0 in it. So, and since we subtracted carnations minus daisies, then we know that the daisies are actually longer, right? And now we'll look at the actual test, the two sample t test for a difference in population mean. So, does increasing the amount of calcium in our diet reduce blood pressure? Examination of a large sample of people revealed a relationship between calcium intake and blood pressure. The relationship was strongest for black men. Such observational studies do not establish causation. Researchers therefore designed a randomized comparative experiment. So the subjects were 21 healthy black men who volunteered to take part in the experiment. They were randomly assigned to two groups. Okay, remember we have volunteers. So we know from chapter 4 that we can establish cause and effect, but we will not be able to generalize our results to the entire population of all black men. 10 of the men received a calcium supplement for 12 weeks, while the control group of 11 men received a placebo pill that looked identical. The experiment was double blind. The response variable is the decrease in systolic blood pressure for a subject after 12 weeks in millimeters of mercury. An increase appears as a negative response. Okay, so this increased blood pressure increased. It looks like it decreased in most of them who took the calcium. This was increase, decrease. Looks a little bit better. So it looks, just based off of this data, like calcium is actually helping with the blood pressure. So we want to know, do the data provide sufficient evidence to conclude that a calcium supplement reduces blood pressure more than a placebo? So we need to carry out a test. So the test is a 2-sample T hypothesis test. And now we need the context for difference in blood pressure. Okay, we need our hypotheses. Our null hypothesis will be that they're the same, right? Our mean of our calcium is equal to our mean of the placebo. Okay, you could have also written it as mu calcium minus mu placebo, right? If you subtracted them, it would be equals 0, right? That says the same thing if you just subtract mu p from both sides. Our alternative is that the calcium reduces blood pressure, right? But it's actually larger because remember, like higher means a positive response. So you could have written it as mu calcium minus mu placebo is greater than 0. Same thing. Then we need to check our conditions. Well, we know that it was from a randomized experiment. They were randomly assigned to groups, so we have random assignment. We need to check the normal with the actual values, right? Since we only have 10 and 11, that's greater than or equal to 5. So it will be, the sampling distribution will be approximately normal if the data looks approximately normal. Well, that looks approximately normal. And with our placebo, that doesn't look bad either. It looks approximately normal. A normal probability plot would be nice. Looks pretty linear. Looks pretty linear. So we can say that the sampling distribution is approximately normal. We will also satisfy our independent condition since 10 and 11 is less than 10% of all black men. And now we can run our test. So we go to menu, statistics, stat tests, a 2-sample t-test, and now we have the data this time instead of statistics. So we have our calcium and our placebo. Okay, our alternative hypothesis is that, remember, our calcium has a higher score than our placebo. And we're not pooling. Okay, we need to write all of this stuff down. Our t-value, our p-value is 0.06, which is close to significant, but not significant. Remember, there's a lot more to that. You need to write all this stuff down. I'm not going to do it to save you some time, but then we can interpret. Since 0.06 is greater than 0.05, we fail to reject the null hypothesis. And cannot conclude that calcium reduces blood pressure. Okay, now remember there's more to this than that, but statistically speaking, it wasn't quite a large enough difference. All right, so we'll do a lot of practice with this in class, but it's really not that bad.